In this video, we want to find the equation of the tangent line to the point x is equal to -1 and y is equal to 3 along the following parametric curve. So we're told the x and y value of a point along that curve, and we want to find the equation of a tangent line to that point. So since we're interested in the equation of a tangent line, the first thing I suggest doing in these problems is just writing out the general form of a line. In this case, we can use the point slope formula of a line that says y minus the y coordinate that we're interested in, or the y coordinate of the point we're interested in, is equal to the slope m times the quantity x minus x0, where x0 is the value of the x coordinate that we care about. So in this problem, we actually know that x is equal to, or x0 is equal to -1, and y0 is equal to 3. So we can take those two bits of information and actually plug them directly into our point slope form of a line. So we have y minus 3 is equal to the slope m at that point times the quantity x minus a minus 1. So just rewriting this slightly, we know that we have y minus 3 is equal to the slope m times x minus a minus 1, or this is x plus 1. So if we take a look at this equation of a line, there's only one thing we still don't know, and that is the m, or the slope, at that specific point along the parametric curve. So we know everything else in this tangent line except for what the slope of this tangent line is. And well, if we think about it right now, when we're trying to find this slope of the tangent line, this is going to depend on the curve itself. So far, we've just plugged in the x and y coordinates of the point we care about along the curve, but we actually haven't used the equations for the curve whatsoever. So the slope is going to basically use that information. So the next thing we do in these problems is, well, identify what in that equation of a line we're still looking for. In this case, it's what the value of the slope is. So let's see if we can figure out what that is next. So the slope, we still think of as a basically instantaneous rise over run type quantity. For us, it's still a dy over dx. However, since we're using parametric curves now, we think about this dy dx. Using our chain rule, we saw in class that this is actually the derivative of our y coordinate with respect to the parameter all over the derivative of our x coordinate with respect to the parameter. So we have the slope m is equal to dy dt over dx dt in this case. So let's go ahead and try to compute that quantity next. So first, if we take a look at our equation of a tangent line, or equation of our parametric curves, our x equation, t squared minus 12t plus 34, we take its derivative with respect to the parameter t, and it goes in the denominator. So let's take that derivative. The derivative of our x equation will give us a 2 times t minus 12. Well, let's take a look at this y equation. When we take the derivative of our y equation, we'll go ahead and put that into the numerator of our slope. So the derivative of our y equation, derivative of 6 times cosine of t minus 4 times pi over 3, if we start with that, we'll get to do a little chain rule here. The derivative of cosine is a minus sign, so we have minus 6 times the sine of the quantity t minus 4 times pi over 3. And then the derivative of what's inside of that cosine gives us a, well, actually just a factor of pi over 3. All right, that takes care of the first term. Now, if we're looking at that minus t squared contribution times sine of t minus 5, we have two functions, the t squared and the sine term, so we get to do a product rule. So if we differentiate that t squared first, we get minus 2 times t, and then times the second function that's there, the sine of t minus 5. Now, if we do the opposite, we'll keep the t squared alone, so we have minus t squared, and then the derivative of sine of t minus 5 is just a cosine of t minus 5. So that is our slope formula for this particular problem. Now, if you take a look at this formula, we basically saw that it's equal to a dy dx, but if you notice this slope, there are no x's or y's anywhere. It's a function of the parameter t. And while that makes sense because we're given a parametric curve, that the x and y coordinates are individual functions of that parameter, in this case t. So at this junction, well, we have the slope formula. What would be really nice is if we had the t value in which to evaluate that formula. But we're given one other bit of information. We can go back to the point that we care about. In this case, if we go back to the point we care about, x and y is -1, 3. Well, what we need to figure out is what t value lands us at x is equal to -1 and y is equal to 3. So that's really our next goal here, finding the parameter value t that lands us at the correct x and y point along that curve. So what this means is we need to find the t value that when we plug it into the x equation, we land at -1, and the t value that when we put it into the y equation, it lands us at y is equal to 3. So more or less what we can do is think about taking either our x equation or our y equation, putting it equal to the correct value of either x is -1 or y is 3, and then solving for that t value. And well, if we take a look at our two equations here, I would think that actually setting this x equation, the t squared minus 12t plus 34, setting that equal to -1, the value of x we care about, it's going to be easier for solving for t in that equation than looking at setting the second equation or the y equation equal to 3. So let's set our x equation, which again is equal to t squared minus 12t plus 34. And let's set that equal to the x value we care about, which is -1. So what we're really asking now is what t value lands us at x is -1. So we took x, the x function, as a function of t, and set that equal to -1. So we're trying to find the t value that works in this case. And well, we cannot factor this quadratic looking thing yet, and we can't just use the quadratic formula because what we need is some parabola or quadratic not equal to -1, but we want this right-hand side to be equal to 0 instead. So we'll just add 1 to both sides of this equation. So when we do that, we get t squared minus 12t plus 35 is equal to 0. And now we have a quadratic equal to 0 or a parabola equal to 0, and we can either use the quadratic formula or we can try factoring this thing. And well, if we try factoring this thing, we ask ourselves, what factors of 35 are there? So things like 5 and 7. So if we took, say, 5 and 7, if we added them together, well, we would get a plus 12, not a minus 12. But what if we take a -5 times a -7? That would multiply to a plus 35. And if we take the -5 minus 7, that would add up to a -12. So it looks like what we can do in this case is factor this into a t minus 5 and a t minus 7. And the product of those two things is still equal to 0. And now in this case, since we have the product of two functions is equal to 0, one or more of those functions is equal to 0. So if we set t minus 5 to 0, we find t is equal to 5. And if we set t minus 7 is equal to 0, we find t is equal to 7. So what does this mean? Well, what this means is we found two t values, t is 5 and t is 7, such that if we put them into our x equation, our x coordinate would be a -1. So we found two potential t values that would put an x coordinate value of our parametric curve at -1 in x. However, we still don't know if that lands us at the correct y value. So we're really wondering now, well, does t equal 5 or does t equal 7 place us at y is equal to 3? So the next thing we're going to do here is substitute those values of t into our y equation and see which one places us at the correct y value. So let's go ahead and do that next. And let's just start with, say, t is 5. So we'll take our y equation in this case. Anywhere there's a t, we'll just substitute a 5 into it, just evaluating the y coordinate at 5. So we have 6 times the cosine of 5 minus 4 times pi over 3, and then minus a 5 squared times sine of 5 minus 5. Let's see what this whole thing reduces to. Again, we're hoping that y of 5 places us at the y value we care about of 3. So let's see what this does. All right, so we have 6 times the cosine of the quantity 5 minus 4 times pi over 3. Well, that just gives us 5 minus 4 is 1. So we have 6 times the cosine of pi over 3. And then we have minus 25 times the sine of 0. And well, sine of 0 is equal to 0. So this whole thing just looks like 6 times the cosine of pi over 3. And well, cosine of pi over 3 is equal to 1/2. So we have 6 times 1/2, which is equal to 3. So this checks out. T equals 5 places us at the right x value and the right y value along that curve. It places us at that point we care about. All right, that to say, we found at least one t value that places us there. There could be multiple t values that place us there. Since a parametric curve, it can do loop-de-loops, and it's possible that just at a future t value, if you will, we just loop through that same point along the curve. So all that to say, we get to do our due diligence and test the other t value as well. So in this case, we'll try that other t value into our y coordinate as well, just plugging in t is 7. So just evaluating our y function at t is 7, we'll get 6 times the cosine of the quantity 7 minus 4 times pi over 3 minus a 7 squared times sine of 7 minus 5. All right, let's see what this whole thing reduces to. All right, we have 6 times the cosine of the quantity 7 minus 4 times pi over 3. 7 minus 4 is 3. So this looks like 3 times pi all over 3. All right, we'll be able to do some simplification there. 7 squared is 49. And then we have sine of 7 minus 5, or sine of 2. All right, let's see what this is equal to. Well, we can see that the 3's cancel out inside of that cosine. So we have this is 6 times the cosine of pi, all minus 49 times sine of 2. And well, you might remember cosine of pi, that's equal to minus 1. So this is equal to minus 6 minus 49 times sine of 2. And what do we want this to equal? We're wondering, is it possible that these two things are, when we add them together, are equal to 3 because that's the value of the y coordinate we care about? Well, let's take a little bit of investigating. The minus 6, of course, is minus 6, minus 49, minus 49. But what is sine of 2 approximately equal to? So let's check it out. If we make a plot, say of x versus sine, This function sign looks something like this, where it's 0 when x is 0, and it goes back to 0 when x is pi. Of course, it's equal to 1 when x is equal to pi over 2 here. And if we're wondering about, well, what x value do we care about? We care about what happens at 2, which, is somewhere in between pi and pi over 2. And if you notice, well, all we can say about the value of sine of 2, it's a positive number, which means sine of 2, if that's a positive number, we have -6 times a -49 times a positive number. We're going to be subtracting -6 minus a -49. Whatever that number is, what we can say about it is that whole quantity, this thing is going to be some negative number. So there's no way it can equal to 3, which means the t-value of t is 7 does not place us at the correct y-coordinate. So we wouldn't include that value. The only t-value that lands us at the correct xy point along that curve is t is 5. So let's take a look at where we're coming from. Why do we care about finding those t-values? Well, we need to find what t-value lands us at the correct point, xy minus 1, 3. Why do we care about that? Oh yeah, we need to figure out what t-value we can evaluate our slope at. Because once we know the slope, we can plug it into our equation of the tangent line. So what's next for us is taking this equation for the slope and evaluating it at t is 5. So we're going to take our formula that we saw before for the slope, put a little notation here. It says, hey, we're going to evaluate this when t is 5. And I'm just going to do this trick where all the t's, because we care about t is 5, I'm just going to erase all the t's and basically just plug in 5's now. It's making sure I don't lose any parentheses in that process. So evaluating our slope at t is 5. Let's see what this reduces to. In the numerator, we have -6 times sine of 5 minus 4 times pi over 3. 5 minus 4 is 1, so this looks like sine of pi over 3 times pi over 3. Let me just start writing that numerator. All right, next, what do we have? We have minus 2 times 5 is 10 times sine of 5 minus 5, which is a 0. Next, we have minus 5 squared, which is 25, times the cosine of 0. All right, that takes care of the numerator. In the denominator, we have 2 times 5 is 10, minus 12, which is something we can compute fairly easily. All right, let's continue reducing this slope now. In that numerator, we have -6 times sine of pi over 3. Sine of pi over 3, well, that's a square root of 3 all over 2 times pi over 3. All right. If we're looking at the next term, minus 10 times sine of 0, that thing is 0. If we're looking at the last term, minus 25 times the cosine of 0 is not 0, cosine of 0 is a 1. So we have a minus 25. Looks like I drew that line too long. All right, then in the denominator, we have 10 minus 12, which is minus 2. All right, let's see what we can reduce here. Well, if we're looking at this 6, we have a 2 and a 3 in the fractions in that numerator. And the 2 times 3, multiply together to get 6, so we can cancel out those factors all entirely. We'll have a 6 over 6. So in the numerator, what this looks like is a minus square root of 3 times pi minus 25 all over a minus 2. And if we wanted to, you might notice every single term in the numerator and denominator, they all have a minus sign in front of them, so we could factor that out of the numerator. So we have a square root of 3 times pi plus 25 with the minus sign out in front. We have that minus sign out in front of the 2 in the denominator, and we basically can cancel those minus 1s. So the slope in this case looks like square root of 3 times pi plus 25 all over 2. So now that we have our slope, we can go ahead and take the equation for that tangent line we had before. Just remind ourselves from before, we had that y minus 3 was equal to the slope that we were looking for, all times x plus 1. So the only thing we were looking for the last few minutes was what that slope was. And well, we just found that slope. So the only thing we're left to do is really just substitute that slope in for m. So we have y minus 3 is equal to the quantity square root of 3 times pi plus 25 all over 2 times the quantity x plus 1. And that would be the equation of our tangent line of that given parametric curve at the point x is minus 1 and y is 3.